Today we shall talk about compound parabolic collectors. Last time we were dealing in general with the concentrating collectors. It seems there is some confusion regarding the maximum concentration ratio. So, I shall go through that very quickly. We will consider a circular concentrator of aperture area A and a receiver area of AR. So, whatever is the solar radiation that passes through the aperture area gets reflected or refracted and gets focused onto the receiver of area AR as shown. In figure 1. So, that shows the sun at a distance of capital R from the earth and of radius r, small r, and the subtended half angle is theta s. So, solar radiation emitted by the sun received on the earth is q s r area A upon r squared by r squared sigma T s to the power 4, where sigma is the Stefan-Boltzmann constant, r is the radius of the sun and r is the distance between the sun and the earth, and T s is the effective temperature of the sun. So, if we write the emitted energy from the receiver to the sun will be A r sigma T r to the power 4 into E r s. If T r is the temperature of the receiver, it emits, assuming it to be a perfect emitter, sigma T r to the power 4 multiplied by A r, the area of the receiver, and a fraction of it, the view factor, will be reaching the sun. So that you have the ratio A upon A r as r squared upon r squared times E r s. That is, under equilibrium conditions, whatever is the solar radiation received by the receiver must be getting emitted back, so that the temperature does not continuously increase. And if you assume maximum value for E r s can be 1, all the radiation emitted by the sun by the receiver can reach the sun, nothing more than that. Consequently, you have A upon A r max equal to r squared upon r squared equal to 1 by sin squared theta s. And if theta s is 0.27 degrees, that is the half angle subtended, then you have A upon AR maximum equal to 45,000. This is for a circular concentrator. We had a confusion last time whether it is for linear or concentrator, which I was responsible for it, because in writing down we started with the derivation for the circular, but somewhere it was mentioned as linear. Since it is sin squared theta s and it will be 45,000, that will be the maximum concentration ratio possible if you have a circular concentrator. Now, the question comes, why is it not infinity? Can I not really focus onto a point? The answer lies in the fact that sun subtends a finite angle, no matter how small it is, 0.27 degrees with the earth. That makes the focus onto a finite area, no matter how small it is. Consequently, this maximum concentration ratio. If it is a linear concentrator, you can see the textbook by Creeth and Frieder, which is a very well written book. AA upon AR max will be 1 upon sin theta s. The max will be equal to 212 if theta s is 0.27 degrees. Though I am writing it as for theta s as 0.27 degrees, we have no option, that is the angle the sun subtends at the earth's surface. So, you have a possible 45,000 concentration ratio for a circular concentrator and a possible 212 as the maximum for a linear concentrator. So, this is what was a bit confusing, in the sense last lecture I was mentioning as circular or linear interchangeably. The whole point is circular concentrator has a higher maximum possible concentration ratio, the maximum being 45,000, and the linear concentrator has a maximum possible 212. So, no matter what your design is, your concentration ratio will not exceed 45,000 for a circular concentrator and 212 for a linear concentrator. In other words, the circular concentrator is not a point concentrator and linear concentrator is not mathematically a line concentrator. It has got finite width, no matter how small it is. So, we have considered the temperature distribution and expressed the useful energy gain from a concentrating collector. We have taken as an example, as shown in figure 4, a concentrator parabolic with a outer diameter being d naught and inner diameter being d I, and of the receiver tube, which the diagram is self explanatory, except I have skipped a certain portion to express the temperature of the fluid as it flows along the receiver tube, which is exactly similar to what we have in the case of flat plate collectors. So, I shall repeat, rather I shall fill in that gap if m dot is the flow rate through the receiver tube And if you consider, as shown in the diagram, an elemental length of dx, the temperature increase over dx multiplied by the mass flow rate and the specific heat is the energy gain while the fluid flows through the tube of length dx should be equal to my f dash, the collector efficiency factor, into concentration ratio times the absorbed energy minus UL into Tf, the fluid temperature, times your area, which is pi d naught, into per unit length. Since dx is over here, I will write it only p d naught, and if I transfer onto the right hand side, you will have the temperature increase due to a length of dx. So, if you integrate this equation exactly like we have done for the flat plate collectors, so the initial condition T f equal to T f I at x is equal to 0. So, you can get exit temperature T f o by setting x is equal to L You can notice that pi d naught into L, length of the absorber tube, is nothing but the area of the receiver, which also can be rewritten as okay. So, this is in terms of the area of the receiver, and if you put CR equal to 1, you will have the same equation we have had for the flat plate collectors. Now, just to be clear, area of the receiver will be pi d naught into L, where d naught is the outer diameter of the receiver tube. Now, we have already derived your heat removal factor should be equal to the actual energy gain, which is irrespective of the governing equations or the balance equations, is nothing but m dot C p into T f o minus T f I, that is the temperature increase of the fluid multiplied by the flow rate multiplied by the specific heat. So, this is the heat removal factor, and by max gain. which we have already explained in terms of TFI. So, we got FR as m dot Cp upon a RUL times 1 minus EXP minus AR UL F dashed by m dot Cp. So, the whole idea of a little bit of this repetition is to say that the area of the receiver comes into the picture, and whereas in the case of flat plate collector, we do not distinguish between the receiver area and the absorber area, which is exactly the same, and we call AC the collector area. So, the solar radiation as received by the aperture area of AA gets reflected and gets focused onto the receiver of area AR, and when we consider the increase in the temperature in the receiver tube, it is the AR that matters, that consequently leads to the heat removal factor being a function of AR being expressed in terms of AR. So, now you have the conventional flow factor defined as FR upon F dashed, which is nothing but m dot Cp upon AR UL F dashed times 1 minus exponential minus AR UL F dashed over m dot Cp. So, the flow factor is again in terms of the non-dimensional flow rate, which is expressed in terms of AR in the case of a concentrating collector. Once again, if you look some books, you will have that the absorbed energy, I thought I should give a clarification over here, IB RB times W minus D naught rho gamma tau alpha beam plus I diffuse D naught tau alpha diffuse upon W. This is the solar radiation absorbed per unit area of the aperture. So, W minus D naught instead of W, which is the width of the absorber, is due to the fact there may be a shadow cast by the receiver tube onto the aperture area, and in this can be rewritten as IB RB times 1 minus 1 upon CR times rho gamma tau alpha direct B plus ID upon CR times tau alpha diffuse. So, this is what you have got in terms of if you consider the shading by the receiver tube onto the aperture plane. And in many instances, if the concentration ratio is high, maybe 5 or 10, it becomes negligible, and consequently AR of course is pi d naught L to reinforce the concept. So, your FR will be m dot Cp sorry, this we have already done it, AR is pi d naught L. So, if IT is the solar radiation per unit aperture area, then IT times A should be equal to A aperture, this is the direct component IBRB, plus receiver area AR times the diffuse component. This is shading by the receiver on aperture neglected. So, consequently, IT should be equal to IBRB plus ID upon CR. That is the received per unit area of the aperture. Okay. So, it receives IBRB, that is straightforward, but a fraction of the diffuse radiation that is directly collected by the receiver should be included in order to estimate IT. Only thing is we are basing it on unit area of the aperture. So, it is to be construed that ID upon CR is the diffuse radiation that falls on the receiver referred to unit area of the aperture. So, it follows the absorbed area should be IB RB, the radiation received, multiplied by the optical factors rho gamma tau alpha direct plus ID upon CR multiplied by tau alpha for the diffuse component of the solar radiation. So, we expressed basically the clarification regarding the concentration ratio for a circular concentrator and the linear concentrator, and subsequently I have also included the derivation of the outlet temperature of the fluid passing through the receiver tube of a concentrating collector, which is necessary to evaluate the heat to mole factor and the flow factor. Subsequently, we also said that there are two ways of expressing the solar radiation per unit area of the aperture. Some textbooks include the shading by the receiver tube onto the aperture plane, so that it will be W minus D naught. Some do not. If CR is 10, 5, that will be a small factor, and the absorbed energy finally is expressed per unit area of the aperture as the direct radiation received multiplied by the optical factors plus a fraction of the diffuse radiation, the fraction being 1 upon CR, where CR is the concentration ratio, and tau alpha D is the transmittance absorptance product for the diffuse radiation. We also have had a brief introduction for what we call compound parabolic collectors. Now, if you look the equations that we have been discussing or arriving at for the concentrating collectors, dominantly take the direct radiation plus a small fraction of diffuse radiation. So, you have got a gain because you track the solar collector with the sun's path or the sun's rays, and direct radiation falling on the aperture can be enhanced, no doubt, but you are losing 20 to 30% even on a bright day of diffuse radiation, because if the concentration ratio is high, the diffuse fraction captured by a concentrating collector will be extremely small. So, the issue has been, can we do something, a design of a concentrating collector which has a concentration ratio, so that the solar radiation falling on the receiver is larger intensity, and it does not lose because the receiver area is small, but also accepts diffuse radiation, which may be 30% of the total radiation. The other thing is disadvantage. On cloudy days, a CC may give you QU 0. If you have a very cloudy day, since it does not accept diffuse radiation, the useful energy gain may be almost equal to 0. So, Winston, Professor Winston, as we have given the reference is 43, that you can see in the companion notes, and he conceived the so called compound parabolic concentrators. Whole idea is to have concentration may not be very high, but enable receiving diffuse radiation and simple tracking. You may recall that we discussed 5 cases of tracking, simplest being east-west axis with one single adjustment per day, such that phi minus beta is equal to delta. The next one, that phi minus beta you keep on changing depending upon the time of the day, still the axis being east-west. Of course, the other 3 deal with the north-south axis and a perfect tracker of 2 axes. So, if you have a simple tracking and then the concentration ratio is not very high, we may get away combining the advantages of a flat plate collector, mainly of accepting diffuse radiation and minimal tracking, yet providing a higher temperature working fluid that is being delivered by the concentrating collector. So, I have shown the picture of a compound parabolic collector. Basically, it consists of the solid lines, let me redraw. these are two parabolas, rather part of two parabolas. This will be continuing like this, this will be continuing like this. So, if this is parabola 1 and this is parabola 2, or this point over here which I will call C and this one B. C is the focal point of parabola 2 and B is the focal point of parabola 1. So, you have got a point on parabola 1 which happens to be the focal point of parabola 2 and the point B is the focal point of parabola 1. And you define, if you cross join like this, 2 theta A, where theta A is the half acceptance angle. It is called the acceptance angle. Any radiation, solar radiation coming beyond theta A shall not be reflected from parabola 1 to parabola 2 or parabola 2 to parabola 1. In other words, only those angles that are within 2 theta A shall be accepted by the concentrating collector and will reach eventually whatever is the focal point B or C, as the case may be. So, I also have shown the coordinate system in the direction of x and the direction of y, and you have got the origin O. So, in nutshell, the two segments AB and DC are parts of two parabolas 1 and 2. AD, let us go back and see, AD is the aperture. Can you show the figure 7 of width W? You can refer to the figure. Then the axis of the parabolas are oriented in such a manner that the focus of parabola 1 is the point C and the focus of the parabola 2 is the point B, which we have already mentioned. And the angle is theta A, 2 theta A, which we have said. Then the area concentration ratio CR W upon W 1 upon sin theta A. So, you can see W small w is the width at the focal point distance will be at small w. The concentration ratio per unit length you can express simply as w upon small w. And with the coordinate system, which you can see in figure 7, right, you can take a little time to look at this picture and copy or do whatever. You can express coordinate y as x squared upon 2 w small into 1 plus sine theta acceptance angle theta a, and the focal length as per the figure is OB. O is the origin where the parabola 1 and parabola 2, they have the axis, vertex of the coordinate system. Simple trigonometric calculation will show you that OB will be equal to W by 2 times 1 plus theta A. So, the points C and D, once again I will show you the figure. C is the focal point of parabola 2 and B is the focal point of parabola 1, whatever, and those coordinates are given by, for C you have W cos theta A, the x coordinate, and B by 2 times 1 minus sin theta A as the y coordinate, and for the point D the coordinates are W plus W times cos theta A and B over 2 times 1 minus sin theta accept angle multiplied by 1 plus 1 by sin theta A whole squared. So, you know the coordinates of the points C and D. So, basically for the purpose of design, you have got two parabolas identical in shape, but a part of parabola 1, part of parabola 2 placed in such a manner, the focal point of parabola 1 will be the base of what is included of the parabola 2 and vice versa. So, now the concentration ratio h upon w, height to the width, which again I will refer to figure. So, the total height is h as shown over here, that is between the points B to A or C to D. It looks like I, but it is h. Half 1 plus 1 upon sin theta aperture times cos theta A, which is nothing but 1 by 2 1 plus C times 1 minus 1 by c square to the power 1/2. So, that C should be the concentration ratio, which we are normally referring it to as CR, but nevertheless there is no confusion as far as this is concerned. So, if you compare surface area to the aperture area, which is nothing but WL, that should be equal to 1 plus C. So, this is established by Parabolic of MIT, and the details you can have from the Solar Energy Journal of 1977. So, if you have the acceptance angle before reaching the absorber surface, that can be expressed by 1 upon sine 2 times theta A surface by WL minus 1 minus sin theta A times 1 plus 2 sin theta A upon 2 sin squared theta A. Well, that's an approximate expression. It's approximate. Exact expression surface area upon the aperture area WL will be sin theta A 1 plus sin theta A times big bracket cos theta A sin squared theta A plus log 1 plus sin theta A times 1 plus cos theta A upon sin theta A plus 2 plus 2 sin theta A to the power 1/2 and theta A times, there should be a plus cos theta A over here, okay, and this is over here minus root 2 cos theta A by 1 plus sin theta A to the power 3/2. Now, I would urge you to take these relations as they are existing. What should be the surface area to the area ratio in the case of a compound parabolic collector? It is expressed in terms of the geometric factor, the angle of acceptance theta A. So, you can refer to any book including Duffy and Beckman by Professor Duffy and Professor Beckman, and you can, if there are any slight differences in the plus minus signs, you can correct it, though I believe I shall include a companion notes as far as the equations is concerned or concerned, and you can have a look at that in case my quick writing has some mistakes, it can be corrected. Now, you have got a compound parabolic collector. This is parabola 1, parabola 2, does not matter whether we called 2 and 1 the other way around. This is the focal point of 1 and this is the focal point of 2. Okay. So, I may have an observer with a tube and a fin like this. So, this will be my aperture area effectively, and this will be sort of my receiver area, which we have called W times L, small w times L, right. The point is parabola 1 and parabola 2 should be inside reflecting. Okay. So, irrespective of this arrangement, I have a ray it should go over here, because this is the 2 1 focal point of 2 and focal point of 1. Similarly, any ray that is coming on to this after multiple reflections will reach the focal point of 1, right. So, depending upon the height, length, etc., how many reflections it will be having. So, people have found rho effective should be related to rho of the surface, that is the reflectivity of the surfaces, to the power m, where m is average number of reflections. This is sort of found out to be about 1.4, 1.5, right. How the fraction is, you can easily imagine. If you consider a large number of rays, and then some of them may be having 2, some of them may have only 1, and the average turns out to be 1.4. Then the significance of the acceptance angle any ray coming beyond this will have a multiple reflection and get out of the compound parabolic collector. Consequently, the theta A is called the acceptance angle. So, solar radiation within theta A only will be reflected, re-reflected, and goes to the concentrating point 1 or concentrating point 2, and then transfers the energy to the fluid. So, acceptance angle. So, that is the significance of the acceptance angle. So, that you will know that any solar radiation ray coming beyond that will not be focused onto the focal point 1 or focal point 2. Now, so this has got, let us say, advantages are simple tracking, say mode 1, what we have considered as east west horizontal axis with one single daily adjustment. Okay. Then it accepts diffuse radiation, because whatever enters through capital W width should reach also the receiver area AR, and reasonable concentration like maybe 3. Now, if you go for a very high concentration ratio with a so called compound parabolic collector, then your acceptance angle will become less and less. Consequently, it will not be accepting the a lot of solar radiation entering beyond those angles. So, something like 3 is okay, which is good enough for 120 degrees C, let us say low pressure steam. At a reasonable efficiency, maybe let us say 40 or 50%. Okay. And this also has got lot of demand particularly in textile industry. So, you got a reasonably efficient collector without going to 3 glass covers and selective coating through the flat plate, but one single daily adjustment you do, a compound parabolic collector, which will give you a reasonable ratio of 3 or 3 to 5 concentration ratio, which is good enough for generating low pressure steam up to 120, 140 degrees C with a reasonably high efficiency of 40 to 50%, and the applications are plenty, particularly one mention I am making is the textile industry. So, everything is so nice, and there has to be somewhere some hitch in this. So, this is one of the very successful designs, but a high accuracy of manufacture is needed. This is not to say that we need not have high accuracy for a flat plate collector or a regular concentrating collector, but the issue here is if you have got imperfect reflectors, it may have multiple reflections and get out and do not reach the focal point 1 or 2. So, you need to have a good accuracy in this optically for the compound parabolic collector. Otherwise, it is a reasonably quite a bright idea to have a low concentration and at the same time produce a reasonably efficient low pressure steam or whatever is the other fluid. So, this is what we have done in the concentrating collectors. First, we considered the several modes of tracking, and then the theory of a concentrating collector through a parabolic concentrator, and then to avoid the disadvantages of a concentrating collector, to combine the advantages of a flat plate collector, a suggestion by Professor Winston had been compound parabolic collectors, which are also commercially successful, and they are parts of two parabolas. One focal point will be at the base of the other parabola and vice versa. That leads to a concentration of about 3, 4, 5, whatever one likes to design, and then you can have a simple this tracking mode, that is only a east west horizontal axis with one single adjustment. So, this expected to be very promising, and quite a few installations are based upon the Winston collector. The slight disadvantage or the concern should be the high accuracy needed in the optics. Otherwise, the rays will not be reflected and going on to the focal points, but they may get out of the compound parabolic collector. That's it. Thank you.